Augusto, 5th grader basketball player. Seems like your average kid, right? You have no idea how not average this kid is, but just to give you some idea, we're going to show you the workout he does every single night from 4 o'clock until 8 o'clock. He dribbles between his legs and makes it look easy. He dribbles behind his back, left and then right, but you ain't seen nothing. How about behind the back and through the legs? He does it over and over till it's second nature, till it's like breathing. How about behind the back and through the legs every which way? How about behind the back and through the legs every which way while he's moving? Hey, hold it. How about 2 basketballs instead of 1? 2 balls dribbling. Maybe 2 balls between the legs. Would you believe 2 balls behind the back and through the legs while moving? Oh, we're just getting started, my friend, just getting started. 2 balls, big bounces and baby bounces behind the back and through the legs. 2 balls, round and round and round and round. 2 balls changing hands every single bounce. All right, 2 balls changing hands every single bounce and not even looking. No, Jay Sean's not average. His dad swears he doesn't push his son into this.
People think that I may push him to do. I don't push him. He actually wants to do it and looks for me for guidance and help to help him get better. It amazes me that he takes it so serious.
He tosses Jay Sean tennis balls to keep his reflexes sharp. Oh yeah, he tosses them while the kid is dribbling. And Jay Sean's ripped too. Maybe the 200 push-ups and 200 sit-ups and 151 leg squats he does before bedtime every night have something to do with it. He plays 2-on-1 against his big brother and his cousin. It's a you make it, you take it format, which can get boring for the other kids. He makes it, and takes it, makes it, and takes it, makes it, takes it, and so forth, and so on.
1, 2, 3, defense!
His 5th grade team is so good they play against 6th graders and beat them. Jay Sean drives in against the tall kids. He is a force of nature.
My goals right now is to be an NBA player.
But you still have no idea just how unusual this kid is. In addition to his crazy hoop skills, he is a runner. He runs a mile in 4 minutes, 50 seconds, which is faster than any 11-year-old has ever run a mile in competition. Jay Sean is expected to break the world record for his age group later this winter. Last week, doctors figured out why this little machine runs so efficiently. His VO2 max was tested. It's a measurement of how much oxygen lungs can take in. Jay Sean tested off the charts. Doctors say they've never seen anything like it. The kid is a freak of nature. And he's this week's little hero.
Okay, guys. So, we're going to take a look at our next section of notes, which is on complex numbers. Okay. Now, this, let me zoom in here a little bit so you guys can see a little better. Hopefully it zooms in. There we go. Nice. All right. You guys have already kind of been prepping for this a little bit because we've been talking in class about what happens when you square a negative number. So this is what's going to lead into it. We'll see how far we get with the notes today, and we'll go from there. So for number 1, solve for x. Our first goal is to get x by itself, so we need to get rid of this negative 3. We're going to do the opposite, which is plus 3 plus 3. Okay. We get negative 2/5 x squared equals negative 4. Now, how do I get rid of the negative 2/5? Okay, hopefully by now we're getting a little more comfortable with this. We're going to multiply both sides by the reciprocal, because this cancels out this fraction. So I get my just x squared on this side. On the other side, though, I do negative 5/2 times this. Okay, negative 4 divided by 2 gives me negative 2, times negative 5 gives me positive 10. Alright, if you need to, you can use a calculator there, but try to do some mental math, it's not that bad. To get x by itself, square root both sides, plus or minus root 10. And much like we've been doing, no big deal, all's well, it's good. Introducing number 2, solve for x. X squared plus 1 equals 0. Subtract 1 over, square root left, square root right. I get x equals the plus or minus the square root of negative 1. Alright. Can't do anything else with it. Going to leave it alone. Move on to 3. Sketch. Y equals x squared plus 1. Now, when I say quick sketch, okay, you guys can take your calculators out if you would like. And all I'm doing here is I'm typing in y equals x squared plus 1. I'm going to hit graph. Let me zoom in a little bit here. Okay, we should see that the plus 1 shifts it up 1. Okay, so what we have here is a graph that looks something like this. Just a quick sketch. All right. Awesome. Now, take a look at this next problem down here. Some quadratic equations such as number 2 and number 3 in the warm-up have no real solutions. What does this mean in terms of the graphs of these equations? Well, take a look. Here's x squared plus 1. Here's x squared plus 1. Here's your answer. Here's your graph. Why do you, well, we know this isn't real, because a negative under the square root cannot be a real answer, okay? So, what do you notice about this graph? Hopefully we see that here is my y-axis and my x-axis. Does the graph of this equation, or this function rather, ever hit the x-axis? It does not. So, in order to have a real solution, our graph must hit the x-axis, okay? The x-axis, the intercepts there, contain your real solutions. Kind of remember when we talked about in class how, you know, solutions, x-intercepts, zeros, they're all the same thing? Well, if it never hits the graph, it doesn't have a solution. It doesn't have a real answer, all right? So what happens is, in order to overcome this problem, mathematicians create an expanded system of numbers using the imaginary unit I. I is equal to the square root of negative 1. Okay? Now, think about this for a minute, all right? There are an infinite amount of answers, or questions out there, that involve the square root of negative answers, because the numbers can go negative forever and ever and ever. So this is actually quite brilliant, all right, to create this imaginary unit I, because what it allows mathematicians to do is to now work with these numbers, which I know you guys are dying to do. When we combine the set of real numbers and imaginary numbers, we get a new set of numbers called complex numbers, written as A plus BI. Now, just to give you guys an example here of what this is saying, something like 5 plus 3i. Okay, that's just an example. The A and the B are any kind of number you'd like in there. They could be negative, but one important thing to note, at least I'm going to try and stress this to you guys as much as I can in class, always try to put the I at the end, like put your constant out front, your normal real number, and then put your imaginary behind it. Just a good way to be. Cool. Now, simplifying expressions. Okay, if A is a positive number, then the square root of negative A is equal to, what you can do is, in order to change this, you can rewrite this as the square root of negative 1 times the square root of A. Now, what do we know the square root of negative 1 is equal to? I. So what we can do is we can write root A I. Okay, and the I is outside of the radicand. Okay, so that's what we're looking at. It's the simplest thing in the world. All you do is every time you see a negative under the radical, you can take the I out, and then you just simplify down your square root. So down here, let's take a look at 4 of these problems together. Root negative 27. What we have here is, the first thing I want to do is I want to rewrite it as root 27 I. I'm just pulling the I out. And now I break it down. What perfect square goes into 27? 9. Okay. What's the square of 9? 3. So I have 3 root 3 I. Okay. Good. No big deal. Now, here I have negative root 25 I. Okay. And what we take a look at here is, you can take the square root of 25, which is 5, negative 5i. All as well. Okay. Notice that it's nothing different. It's just you're literally taking the I out if there's a negative underneath it. So please see how simple that is. Here, negative 36 divided by negative 49. And again, I'm going to pull the I out back. But now, what's the square root of 36? 6. What's the square root of 49? 7. 6 over 7i. Okay. And lastly, trying to figure out a perfect square that goes into 72. I think, well, first, pull the I out. Okay. And then I can break this down to 36, root 36 times root 2. Square root of 36 is 6. 6 root 2i. Are all good. Okay? So, for right now, we're good. I'm going to give you guys a little bit of practice with this, but at the moment, try breaking down perfect squares. Make sure you're pulling the I out. We'll be in good shape. Okay? So, as always, keep up the good work and good luck. We are all counting on you.